Section 14.5, Directional Derivative and Gradient Vectors. This would be the same as 14.6 in Stewart's textbook. The purpose of this section is to find the rate of change of a function of several variables at any direction. Remember, the partial derivative of f with respect to x was rate of change of the surface in the positive x direction, and the partial derivative of f with respect to y was the rate of change of the surface in positive y direction. So in this section, we like to generalize those partial derivatives to any direction. So remember the derivative, the definition of partial derivative of f with respect to x and f with respect to y. Notice with respect to x, we had to increment x's but keep the y's constant. With respect to y, we had to increment the y's but keep the x's constant. Okay? But in directional derivative, notice x's and y's gets to be incremented. In other words, neither of them are kept constant. So this is the definition of directional derivative of a function of two variables at point x0, y0 in the direction of unit vector AB. Notice this has to be a unit vector. The notation is capital D, F with a subscript U, which this stands for directional derivative of F within the direction of unit vector. This is the definition. F of x0 plus HA plus y0 plus comma y0 plus HB minus f of x0 y0 divided by h. You take the limit. If this limit exists, then you have obtained the directional derivative of this function at that specific point in this direction. Notice this represents the rate of change. Therefore, the answer is a number. So it's not a vector, as you always get a number. In other words, this quantity gives you what? How fast the surface is changing at any specific point in a given direction. So, special case of directional derivative, if the direction which you selected happens to be I, and that changes the what? Directional derivative formula to partial derivative of f with respect to x. On the other hand, if you happen to choose what? J, which is a unit vector in the y direction, guess what? If you kind of substitute 0 for A and B for 1 in the definition of the directional derivative, you get what? Partial derivative of f with respect to y. So in other words, the bottom line is directional derivative is generalization of partial derivatives of f with respect to x and y. However, for computational purposes, we don't use the limit. We use this formula, which is partial derivative of f with respect to x times a plus partial derivative of f with respect to y times b. Then again, don't forget, this always comes up as a number, not a vector. So just to make sure this is clear, we're going to introduce a differential operator called del operator. So it's like upside down triangle. Is a vector which what? Its components are partial derivatives. Remember, these are blank partial derivatives, so they don't mean anything. This is just an operator, okay? And it's read del, some people call it nabla. So for function of, let's say, 3 variables, so the answer is a vector. So you got blank partials for x component, y component, z component. If we apply this operator to a function, then the answer is a vector whose components are partial derivatives of that function respectively, like with respect to x, with respect to y, and so on and so forth. So this notation del f is called gradient vector of the function f of xy. So this guy is called gradient vector. All right, so so the idea is this. Now that we know what gradient is, so now we can what? Rewrite the formula, which was right over here. Okay, this formula right here. In terms of del operator, in other words, that would be the same as what? Gradient of f dotted with unit vector. So that's what this is. Gradient of f, okay, gradient vector of f dotted with u. Remember, that's a scalar. Remember, u is a unit vector. So let me show you an example so you guys can see how this works. Find the directional derivative of this function, e to the xy minus y squared, in the direction of this guy, this vector, at this point. Remember, this is not a unit vector, so the first thing you have to do is what? Convert this immediately to a unit vector, because the formula has a unit vector in it. Do you see it? So what are we trying to do? We're trying to find the rate of change, how fast the function is changing at this point in this direction. So the first thing, as I mentioned, what is change the vector into unit vector. So take vector b divided by its magnitude, there it is. Now find the gradient of the function fxy. Remember, gradient is applied to a scalar function. What is it in this case? It's a vector whose what? X and y components are partial derivative of f with respect to x, partial derivative of f with respect to y, respectively. So if you take the partial derivative of this function with respect to x, you get this. And with respect to y, you get this. However, if you evaluate this gradient of vector, at 2, 2, you get 2, negative 2. So now you are ready to find the directional derivative of f in the direction of u at point 2, 2. So take this gradient, which is 2, negative 2, dot it with unit vector, which is this, and lo and behold, you get an answer. Because the answer came up positive, so that means what? The rate of change is increasing. Okay, so we have an increasing rate of change of that function at this point in this direction. Do you see it? So notice at the end of the day, we always come up with a number. All right. So what would be the properties of what? Of gradient. The gradient of sum or difference of two functions is the gradient of what? The sum and difference of gradient of each. The gradient of constant times f is constant times gradient of f. Gradient of f times g, you have to use product rule, is f times gradient of g plus g times gradient of f. Gradient of the ratio of two functions, you have to use quotient rule. So you kind of go g times gradient of f minus f times gradient of g over g squared. If the unit vector makes an angle theta with positive x-axis, then the unit vector can be expressed in terms of sine and cosine. How is that? If this is the unit vector, which makes an angle theta, and let's say its components is x and y, so x is 1 times cosine of theta, and y is 1 times sine of theta. So therefore, the idea is, in case you know what angle u makes with what positive x-axis, then the rate of change of the function with respect to u is gradient of f dotted with, excuse me, unit vector, but the unit vector in this case is what? cosine theta times sine theta. Do you see it? Okay. So one of the burning question in this section is, of all the possible directional derivatives of f at a given point, in which of these directions does f changes fastest or slowest? And what is the maximum rate of change of the function? And what is the minimum rate of the change? So in other words, directional derivative represents what? Rate of change of the surface at a given point in a given what? Direction. Of all those directions, in which direction the rate of change what? Changes fastest or slowest? And if so, what would be the maximum rate of change or minimum rate of change? Remember the definition of what? At least the formula we use for what? Homework purposes. Directional derivative of f in the direction of unit vector u is gradient of f dotted with unit vector. But remember from previous chapters, I can write this dot product as what? Magnitude of the gradient of f, magnitude of u times cosine. U is a unit vector, so its magnitude is 1, so you get what? Directional derivative of f in the direction of u is magnitude of the gradient vector f times cosine theta. This guy will be maximum if cosine is 1, because remember cosine goes from -1 to 1 as theta varies between 0 and 2 pi. So the maximum value of the cosine is what? 1. Okay, that happens when theta is 0 or pi, correct? So if this is 1, so the directional derivative is what? Is magnitude of the what? Gradient vector. So this is a scalar, and it represents the maximum rate of change of function in the direction of u at p. So this guy gives you the maximum rate of change. So the maximum rate of change of a surface in at a specific point in what? In a given direction is magnitude of the what? Gradient vector. And this magnitude rate of change occurs when u is what? Has the same direction as the gradient vector. In other words, u has to be parallel to what? To gradient vector. Remember, theta was 0. So the angle between what? If the angle between u and the gradient is 0, 0 or pi, so that means what? They are parallel. So u is parallel to the gradient vector as theta is equal to 0 or pi. So the maximum rate occurs here. That's a number, which is the magnitude of the gradient of f. And in which direction that maximum occurs? In the direction of the gradient vector itself. In case you were interested in minimum, this would be negative, and the direction will be opposite it, which would be negative gradient of f. So with that said, let's take a look at this example quickly, and then we should be a-okay. So given this function, tangent of x plus 2y plus 3z at point -5, 1, 1, find the maximum rate of change at point P and the direction in which this maximum rate of change occurs. So what you need, or what we need to do to answer part A, is find the magnitude of the what? Gradient vector. So here's the gradient vector. Remember, the gradient vector is what? Partial derivative of f with respect to x. So it's a vector whose components are partial derivative. And this guy is partial derivative of f with respect to y. So you get what? With respect to x, and this guy is partial derivative of f with respect to z. Okay? So derivative of tangent is secant squared. Derivative of x is 1. Derivative of tangent is secant squared. Derivative of 2y is 2. Derivative of tangent is secant squared. Derivative of 3z is 3. if you evaluate this at a point, given point -5, 1, 1, you get gradient is equal to 1, 2, 3. So the maximum rate is what? Magnitude of the gradient, which is square root of 14. So this is the maximum rate. Question, in which direction this maximum rate occurs? In the direction of the gradient. What was the gradient, direction of the gradient at point P? 1, 2, 3. There it is. So maximum rate is a number, but the direction in which the maximum rate occurs is a vector. So as I said, in case we are interested in minimum rate of change, so take negative of the magnitude, and the direction will be negative of what? Gradient vector. So here is a nice question, problem. An ant at point 1, 1 wants to walk in the direction in which the temperature drops most rapidly. Find a unit vector in that direction. Given the temperature at any point x comma y on a metal plate in xy plane is given by this function in terms of Celsius. So this would be temperature of any point on the metal, hot metal, is xy divided by 1 plus x squared plus y squared degrees Celsius. To find the direction, that means to find the unit vector. Okay, so how do you find this? That would be what? Gradient of the temperature divided by its magnitude. The reason I have the minus here because it says at which temperature drops most rapidly. Drops means negative. So what you have to do is what? Find the gradient. Evaluate it at 1, 1, you get 1, 9, 1, 9. Find its magnitude, which is this. Go back here. I replace this guy with vector, this guy with a number, and lo and behold, what? This is the direction right there in which what? The temperature drops, remember, drops most rapidly. Before we end this video, I'd like to kind of mention a few highlights of gradient, and then that should be the end of it. What is the significance of the gradient vector? A couple of important results we notice from this section. The gradient vector gives the direction of the fastest increase. If you want the slowest increase, then it will be negative. The gradient vector is always orthogonal, which is the different word for perpendicular to the level surface through a point. Notice this is the what? This is any curve on the surface. This is like the tangent vector. The gradient vector is always perpendicular to tangent vector at any given point on the surface. So this would be like level surfaces, correct? So, so when you have function of x, y, z is equal to constant, that's what? Function of 3 variables. So those will be like level surfaces. In other words, the gradient vector will be perpendicular to the level surfaces at any given what? Point. If the function is function of 2 variables, then we don't say level surface, we say level curves. And then again, here is a level curve, here's the tangent line. Notice the gradient is perpendicular to the what? Level curve at point P to the tangent vectors. So what happens is, if this is topographical map of a hill with what? Fxy representing the height above the sea level at a point xy, then the curve of steepest ascent or climb can be drawn, there it is, what? Making it perpendicular to all the contour, what? Lines. Notice these are all what? Perpendicular to all the level curves. These are what? Kind of like driving the point home that what gradient vectors are perpendicular to the level curves at any given point on the curves, or in this case, surface, that is. If we plot gradient vectors, you know, starting at point x0, y0, such a plot is called gradient vector field. For instance, if you graph what level curves for x squared minus y squared, which you could do that by setting x squared minus y squared equal to k and replacing k with what bunch of numbers, you get all these curves. If you draw the what gradient, or if you compute the gradient vector at any given point on these level curves, notice they are perpendicular to the what level curves at any given point. Also, this clearly shows that what gradient vectors point uphill and perpendicular to the level curves. So notice these guys are perpendicular. Do you see it? And they point uphill because this guy represents the what? The fastest rate of change of the function at any specific point in a given specific direction. Thank you.